All right, so first lecture in thermal systems design, we're covering piping systems. It'll be a while before we're out of chapter 1. It's actually a long chapter. It's a very important chapter. It's not just a slough introductory chapter, so please spend some time in it. And then we'll get into heat exchangers. So all of this prerequisite materials fluids, which is a prerequisite to heat transfer, which is a prerequisite to this class. So spend some time in it. Also, one thing is this textbook uses inches, feet, pound force, etc. Let's just use it, okay? It'll take you a little bit, but until the world really switches, or the United States really switches to SI, there's sure a lot of inches and feet and other units used both in practice and every day. Go to the grocery store and look, as well as in engineering. A lot of engineering calculations are still done. Fluid density. We talk about the mass density. What symbol do you like to use for that? Rho. And we will give the SI as well as the United States customary system of units to help you refresh your memory. So SI units for mass density, something like kilogram per meter cubed. But what about over here in the United States? What that is still, this is what you might call the imperial, British, English. I don't like those terms. I say in the United States, we're the only ones still really using it, customary system of units. What would it be for mass density? What is it? I heard a couple, but I didn't hear clearly. So a pound mass per cubic foot. Just a little thing, is that M subscripted or not subscripted? Is just LBM without a subscript? Yes, that's the typical way it's done. And somebody may have said slug per cubic foot, right? In the United States, do you buy anything in slugs? Somebody, if I said, can you please tell me your weight? Do you think they would tell it to you in what units? Or whatever, they'd be pounds. Be pound mass. So forget the slug. I'll come back to that if you like and talk more about the slug. We should know something about the slug, but then there's another term called gravimetric density. Maybe the textbook doesn't use this term gravimetric density, but what do you think that is? It's in the fluids book. What is it? Specific gravity would be something like comparing to water's density, and so if it had a specific gravity 1.1, it'd be denser than water. It would sink and not float. If it had a 0.8, it would float, right? So not that dimensionless ratio of densities. But gravimetric, what does gravimetric imply? Gravity, right? So I even stumbled a little bit because I said, if I asked you your weight, you would report it to me in units of weight, which are pound force. So this is, if I could help here, it's pound force per cubic foot. So if I have a cubic foot of this stuff, this fluid, what is the weight of it? What is the force that I'm going to need to apply to hold it up instead of letting it go and it's going to free fall toward the center of the earth, right? That's what weight is. So the weight, if I said, here's a chunk of mass M, and I want you to calculate the weight, how would you do it? How would you finish this equation? You would multiply by G, and G is the gravitational acceleration for the Earth. It's 9.81. If they go to the surface of the moon, it's a little different, right? Okay. 9.81 meters per second squared. 9.81 meters per second squared. Oh, I forgot. What is it in the United States customary system units? It's a 32.2. Sometimes you'll see me do 32.174. The textbook does that sometime too, but right where we're at, we don't know G to that many significant digits. So I challenge students in Thermo 1 at times. You know, you can find out exactly where UTSA is, where San Antonio is. calculate G at that location, then go and get it somewhere in Colorado or somewhere down in South America and somewhere in India or somewhere, and it'll be different values. It won't be 9.81 or 32.2. So, but every now and then we'll use the 32.2. Are these the right units? Is it really foot per second squared, or is it foot squared per second squared? What is it? Is this right? Yeah, it's right. True. All right, so gravimetric density, given the symbol gamma, which is rho g, that's how you calculate it. And in the SI units, rho times g would give you how much weight there is per cubic meter. So what do I put here in the numerator for the SI units for the gravimetric density or the weight density of a fluid? Newtons. So newtons per cubic meter or pound force per cubic foot. Okay. Pipe flow. So we have a pipe, and the pipe has diameter d. True? And so what is the cross-sectional area that the fluid flows across as it's going down the pipe? What is that area? Pi d squared divided by 4, is it not? Yeah. Now, we want to talk about the flow rates. We can talk about the mass flow rate, volumetric flow rate, gravimetric flow rate. 3 flow rates. And then we can talk about both SI units as well as US customary system units. So what symbol do you think would be good in general for mass flow rate? M dot. And SI would have units of kilograms passing some location, crossing that cross-sectional area per second. What about United States customary system units? We're talking about mass flow rate. LBM per second, pounds mass per second, true? Now, what about the volumetric flow rate? Some fluids textbooks use a cap Q. Maybe you used a fluids textbook that had a cap Q for volumetric flow rate. I think this book, embedded some places, does fall back to a cap Q for volumetric flow rate. So it's common, although I prefer to use AV, the product of what? Some mean velocity times cross-sectional area. That gives me the right units. AV is the volumetric flow rate. I prefer that. So what would be the volumetric flow rate SI units? So it's how much volume passes that cross-sectional area per second. How much volume of that fluid, meters cubed, passing it per second. How about volumetric flow rate in United States customary system units? Cubic feet of volume, cubic foot, foot cubed per second passing across, that cross-sectional area and going down. Gravimetric flow rate. Professor, why do we need all these flow rates? Because they're used. They're used, okay? So it's not that hard. So what are we talking about? What symbol? Well, there's really not a great symbol for it. But how would you calculate it if I said calculate the gravimetric flow rate? Well, it's not going to be the mass per unit time. It's going to be the weight per unit time. Right? Actually, this makes a lot of sense if you had a pipe and you were able to divert all of the flow into a container and then have a stopwatch and start at time 1 equal to 0 and stop it at time 2. That's how much time went by, and it filled this up. You would then probably put it on what we call a scale, and that scale would measure basically the mass, or it would measure the weight depending on how it's set up. It's probably going to infer the mass from a weight calculation. True? So you'd be saying, how much, how fast is it filling this up by diverting that flow to a measurement? So you really, this gravimetric flow rate's not too absurd. It's pretty logical, actually. How many pounds of material per second go down there? But we're not talking pound mass because that was a mass flow rate. What would it be logically for the gravimetric flow rate? Pound force. At first you think, what? But you and I, it's like, it makes sense. It's a pound of weight, that's how we measure a pound. A lot of times you just drop the distinction. You just say it's pounds as a plural, lbs. Okay, so it's pound force per second. What would be the gravimetric flow rate units for SI? Newton per second. Less common. But it still makes sense. What would be a symbol for this? I don't know, but just like I used volumetric flow rate as a product of AV, what would you multiply m dot times to get the gravimetric flow rate? G. G. Now, I don't know if I should divert here and talk about G for a minute. Let me do that. I'll go ahead, and it's the most logical place for it. What is G? So, two things. You could say, if I take an object and I let that object free fall, surface of the earth, it will accelerate at a certain rate. What will be its acceleration rate? Neglecting wind resistance and whatever there's no other pull to it. It's just gravity's going to, taking this object, I'm going to let it go. It experienced some acceleration. It was free falling to the surface of the earth. What was its rate of acceleration? That's right. It was the 9.81 meters per second squared in the SI units. And in the United States customary system of units, it had experienced a free fall acceleration of 32.2 foot per second squared. Now, somebody says, gee, a lot of stuff in engineering isn't free falling. Most of the time it's just sitting there. And to hold it there, we got to support it. In a building, they got to support it. The floor's got to support the weight. The pipe has to be strong and has to be supported by supports. You'll see them all over the place. So in most engineering calculations, we don't let things free fall. And so we have to support it to compensate for the object's weight. So there's a big equation, we've already seen it. W is equal to mg, isn't it? So it just is stationary. But it needs to be supported. So then you ask yourself, well, G, in this case, this is how I get the weight from G. G really is W divided by M. That's what G is. Most of the time we should think about not acceleration. We should say it's the weight per unit mass, surface of the earth. That's my definition of G. Take out acceleration. I remember when I was a student, it's like, I'm using it all the time, and the thing's not accelerating. I'm just using G to calculate the weight of something. Why do I call it acceleration? Because if I let it go, if I didn't support it, it'd free fall. So let's do this. Let's say that we know that G right here is 9.81 meters per second squared. I'm going to write an equation, 9.81 meters per second squared. Did I make an error in any calculation up until this point in that equation? Is that equation good? Do you like that equation? Let's do the mathematical trick of playing with only one side of the equation and obeying all rules of math so I can multiply this side by 1 and it won't change anything, true? If you recall, 1 Newton is 1 kilogram meter per second squared. Where did that come from? You have it tattooed on your body. It means something. You have it ingrained in your memory. This is a 3-stroke equation. What does that 3-stroke equation mean? It's defined as. That's what a Newton is defined as. So I can take that 1 and replace it by a Newton divided by kilogram meter per second squared. Did I make an error? Or do you agree with that step? Thumbs up, you agree. All right. So if I take and cancel here and cancel there and cancel here and cancel there, guess what G is? It's not 9.81 meters per second squared. It's 9.81 newtons per kilogram. And that's the way we normally, or we should more often think about it, 9.81 newtons per kilogram. That's what G is. Okay, here's the prize, right there. You got to do exactly the same thing. That's why I went slow. Exactly the same thing to find out what G is in the United States customary system of units. Well, we're thinking about something that's stationary, that's not falling, that's being supported. The weight of the object or some mass is being supported. That's the whole goal here. So let's do this. Can we start out with 32.2 foot per second squared equal to 32.2 foot per second squared, and then multiply by 1? Will that work? Is that strategy the same as what we just did? Yeah. What's the 1? Oh boy. Well, what's the cousin of this equation in the United States? There it is in SI. What's its cousin? Something about a pound force, something about a pound mass, something about a foot and a second squared. Is this equation, should I just put a bar in there, just say like 1 is 1 is 1 is 1, and call it quits? Nope. Nope, 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 nope. Somebody already got it. They said, hey, there's a 32 floating around. Okay, help me remember, where's that 32 go? Does the 32 go right here, 32.2, or does the 32.2 go on this side? Look, it's only 2. Professor, I was so close. I was just off by the inverse. You don't give me much partial credit. Come on now. Cooperate with me. I want to pass. Which one is it? With confidence. You're going to graduate soon. Aren't you already interviewing for jobs? Did I tell you out there what's going to happen if you get a job in a company, right? There's other experienced engineers or some really experienced technicians. And they're a little upset just because there's a thing called salary compression. That means they ain't making much more, probably sometimes less than you, the new hire. So, what are they going to do? Yeah, they're going to throw out some things, and then as soon as you flub that answer to that simple question, down the hall they go, broadcasting to everybody in the company that they have just made the colossal mistake of hiring the biggest idiot. True? Anybody worked in a company? Anybody seen that type of... it can happen. It can happen. So we got to get this right. You had it right. So help us. Walk us through it. Yeah, but you're not helping me. Give me the logic. Give me the logic. Okay.
You have to cancel the units. That's my...
Okay. All right. You know what? I really feel strongly that you need to own this as a class. And every member in this room needs to own it. So what I'm going to do is that's a teaching strategy of not telling you the answer. Because it will force you to go get the answer. And when you get it, you won't tattoo it on your arm or your back of your neck or wherever you tattoo stuff. You're going to put it in your mind and you're going to own it. And I really feel strongly something simple as this. If you've had me before, I tried to cover this typically in a class or two. It's nothing that I've tried to hide from students. But at the 4,000 level, let me just say you need to work it out. All right. The answer. Who knows the answer? Don't shout it out. Just raise your hand. You know where I'm going with this? Nobody? All right. Who's taken a class with me before? Ooh, I'm humbled. I'm humbled. All right. Let's keep on. So, we have reviewed about gravity, and we see that the gravimetric flow rate is a product of G times m dot. All right. Bernoulli's equation. Who's heard of Bernoulli? Everybody's heard of Bernoulli. Can you write it from memory? Yes. You want to get that way. So, how many people remember it? Who wants to be my volunteer? that will recite for the class Bernoulli's equation from memory, no book needed. Come on, who's going to be the volunteer? I humiliated you, sorry. You're going to clam up on me. Nobody's going to. All right, Jeffrey, go. You got it? Yep.
Pressure plus 1/2 velocity squared plus rho gz. Oh, rho v squared, sorry. Rho g, and then the other side is g2.
How's that? So it's a constant, isn't it? The sum of three terms, pressure is the normal way most students remember it, plus 1/2 rho v squared, which when you work the units has units of pressure, plus rho gz, when you work the units has units of pressure. The sum of those three pressures is a constant. True? There's a number of assumptions. I can apply Bernoulli's equation, steady flow. All right? Another assumption. Along a streamline. Follow a pack of fluid. It's going to go along a streamline. Right? Another assumption. We typically treat only incompressible. You can get a more beefed up, steroid version of Bernoulli's equation that handles the compressible effects. Not in this class, typically not in your undergraduate fluids class. So it's incompressible. Last one? No viscous effects. So frictionless is one way of saying it. And I think coming from a lot of applications. Or you could say inviscid, no viscosity, negligible viscosity. So you apply it along a streamline. We're going to do this engineering calculations, or a lot of them in piping flow simulations, etc., analysis are based on this Bernoulli's equation. So we follow a chunk of fluid, etc., along a streamline, and something remains constant. Bernoulli's equation. Can you fill this in? Fill in the blank. Bernoulli's equation is a statement of the conservation of, don't shout it out. I'm going to pause and I'm going to walk around because I need a little exercise. I want to see what you write down for the fill in the blank on this. So a lot of people put the word energy there. But is it of all forms of energy? That's the word I'm looking for. The mechanical. Yeah, I can't spell. Come on now. Mechanical energy. But you can have different forms of mechanical energy. True. True. That's why we had that. So the last two are the easy ones. The rho gz. You would say that's what type of energy? Potential. Gravitational potential energy. That is a pure mechanical form of energy. That 1/2 rho v squared, what type of energy? Kinetic energy. Kinetic energy. Often we burn to push and motivate, turn and accelerate to get it into that nice form of mechanical energy. We do a lot of things to get the mechanical energy, and then we see it wasted through friction and viscosity and a lot of other things. But this term, what? That's a mechanical form of energy? It really is. Pressure, force per unit area. And you can think of something kind of like a balloon expanding or something. That's a really good form of mechanical energy. So there you go. Well, if Bernoulli's equation is a statement of the conservation of mechanical energy, we should be able to interpret those forms, those terms. And so if you write it in the Bernoulli's equation in terms of pressure, like we just did, it was P plus 1/2 rho v squared plus rho g z is equal to a constant along the streamline, steady state, inviscid, incompressible. This would be the pressure. This is another type of pressure. What type of pressure is that one? 1/2 rho v squared. That we said it was due to the kinetic energy. Velocity pressure or dynamic pressure is the term often. 1/2 rho v squared is either the velocity or dynamic pressure. And we said so you can see how you can interpret this kinetic energy in the form of velocity pressure, or dynamic pressure. What does rho gz look like? If I didn't even have it in Bernoulli's equation, I just said, here I have some tank of water, and from this depth down, rho gh, rho gz, the depth in the water, what would that be? It's static, hydrostatic. Hydrostatic. Let me put a hydro on there. Pressure. So those three pressures can be interpreted in terms of energy. But, oh boy, those units, every one of these, if you're thinking of it, either has a SI unit of a Pascal or kilopascal, which is a Newton per meter squared, or in the United States customary system units, what would it be? It would be something like lbf per foot squared. PSI, pounds force per square inch, or pounds force per foot squared, right? How do you get that to be an interpretation of energy? How do you interpret pressure as an interpretation of energy? It's not too hard. Do our one trick, which is if I put a meter here and a meter there, a joule is a Newton meter. Is it not? Is a joule a Newton times a meter in SI? So you could say that in SI, it's a joule per meter cubed. It's energy per unit volume. That's how you can interpret pressure. Energy per unit volume. Okay. Let's continue it in the United States customary system units. I take and I multiply by what? What do you think I multiply by? Something over something. It was meter over meter before. What do you think I'm going to do right here? Foot over foot. Foot over foot. You say, well, you got the cubic foot right. But I sure don't understand what is a pound force times a foot. Is that a unit of energy? Mechanical engineering students all in unison say, you bet your life it's a form of energy and unit of energy commonly used out there. Pound force times a foot. LBF times a foot. We'll get on to more. You'll get more up to date. Now, let's say we take Bernoulli's equation and somebody says, you know what? Why don't I take Bernoulli's equation and divide everything by rho? So what I'll have is I'll have pressure over rho. I'll have 1/2 v squared, and I'll have gz, and you know that's equal to another constant, not the same constant, but I'm not going to say C1 and C2 and C3, but it's C divided by rho. And I look at that, and I say, you know what? Every term in that different way of expressing Bernoulli's equation has some units. If I look at the SI, maybe it's easiest to focus on this term right here. If I look at the SI units for it, isn't it meters squared per second squared? And then one of the things that you learned in Thermo 1 when you studied energy and all that, you said, oh, 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram. Remember that unit conversion? Even if you don't remember it, somebody could say, why don't I take this equation and multiply by kilogram over kilogram? Did I change the equation? Nope. But then I say, what is a kilogram meter per second squared? So a Newton is a kilogram meter per second squared. Bye-bye that kilogram. Bye-bye those seconds squared. Bye-bye one of the meter. And then I multiply by another one, which is a joule is a Newton meter. Maybe I change color. Newton, bye-bye. Meter, bye-bye. What I end up with is joule per kilogram. Isn't that energy per unit mass? Bernoulli's equation can be written this way, and each term can be interpreted as energy per unit mass. What would it be in the English? It would be, well, we could work it out. Doesn't matter how we do it. Maybe I need more room to do it. I'll do it right here. Let's start with, If you want to start foot squared per second squared, you can do it that way. What would I multiply by? Multiply by pound mass divided by pound mass. Then I need to multiply by the thing I told you I wasn't going to tell you and that you had to figure out on your own. Or it needed to be remembered, you needed to remember it with confidence. Maybe you already forgot the question. I hate to ask a question, say I'm not going to answer it, 2 slides later answer it. Okay, so what is the unit conversion factor that you need? So 1 pound mass at the Earth's surface, 32.2. Actually, this is even slicker. Let's do it this way. Pound mass, 32.2 foot per second squared is a pound force. So I know it's you can do it a little cleaner, but you get rid of that foot, second squared. I have the unit of pound force times foot, that's energy, per pound mass. Yes, it's energy per unit mass. How did I go from this equation to that equation? Just divided by rho, multiplied by 1 over rho. There's another, you could take Bernoulli's equation and express it in terms of not pressure, not energy per unit mass, but you could express it in terms of head. How do I do that? Well, I'll take the original equation and divide by rho g. So I'll have, the equation will be P divided by rho g plus V squared over 2g plus Z is equal to a different constant. Have you seen Bernoulli's equation written in any of these 3 forms? Yeah. So you can interpret this head in units of, just look at the units on this term right there. It's in terms of meters. But if I multiplied by Newton over Newton, what's a Newton times a meter? Joule per Newton. That's not so easy to interpret. Joule is energy, Newton is weight. Energy per unit weight. That's what a meter is. That's what a head is. It's a measure of energy per unit weight. Okay, let's do it over here for the SI, not the SI, United States Customary System units. What would be Z? It would be feet. Just multiply pound force divided by pound force. So we got a pound force times a foot. That's a great unit of energy per pound force. Great unit of weight. So when you look at Bernoulli's, you could write it 3 ways. Pressure interpreted as energy per unit volume. Energy per unit mass, sometimes they'll just say head. But often if they say head, they really don't mean energy per unit mass. They really mean elevation or energy per unit weight. All of these are energy per unit something. Head is energy per unit what? Weight. All right. Now, fluid power. So you could think if I have energy per unit volume, that was pressure. And I multiply volume per unit time, the volumes cancel and I have energy per unit time, do I not? Energy per unit time is power. Power, isn't it? Okay. So if I have something, maybe I should put it in terms of a pump. I have fluid coming into the pump, going out of the pump. Something changes across the pump. The most logical thing that you and I would talk about changing across the pump is the pressure. The pressure is changed across the pump. True? Somebody says there's some power being supplied to the fluid. Okay? That power being supplied to the fluid, sometimes it'll be like this, W dot into the fluid, is equal to the product of the pressure change energy per unit volume times something. What is the volume per unit time? We've introduced it before. What is that volume per unit time? Volumetric flow rate. What symbol did we use? AV or Q. I like to avoid Q, but it's Q or AV. What about if I wanted to calculate the fluid power, not in terms of the volumetric flow rate, AV, but I wanted to calculate in terms of the mass flow rate? Well, there's a couple ways to do it. Think about this. Energy per unit mass times the mass per unit time. Well, this one's easy. The mass per unit time is the mass flow rate. What do I multiply it by? It's that change in the energy per unit mass of my flowing fluid. Go back to this one right here. This was my energy per unit mass for my flowing fluid. Some of those three terms, sometimes they'll have where this is maybe cap H. And this is a lowercase h. Cap H for head, where they mean energy per unit mass, and lowercase h for head, where they mean energy per unit weight. So something changes. Maybe there's a change in the cap H. The energy per unit mass, that would be W dot fluid. Okay, last one, gravimetric flow rate. Well, gravimetric flow rate was G times M dot, right? So you have G times M dot times the change in some, maybe I put lowercase h there instead of Z. Some change in the head. How was that head interpreted? Energy per unit weight times the weight per unit time. This change in head, energy per unit mass, times mass per unit time. This change in pressure, energy per unit volume times the volume per unit time. All right. Now, there's a little distinction between the power supplied by a shaft to that fan or pump, coming in like this, and what actually gets into the fluid. I like to call fluid power is shaft power. The device called the pump, you feed it shaft power. You want it convert all that power into fluid power, but it's never 100% conversion. So we have some efficiency of the pump, which is the ratio of what gets into the fluid divided by W dot into the shaft that drives it. That's some efficiency. Now, if you had a motor, you would just back it up and say, I'm supplying electric power. The motor tries to convert all that electric power into shaft power. I have another efficiency of the electric motor. And you can stack those efficiencies. So we have the pump efficiency there. Modified Bernoulli's equation to account for losses and gains. So what we do, we have a piping system. We're going to go from this location to that location. Maybe I should show it as doing this. Changing elevation, going from state 1 to state 2. Along the way, we have some head losses, some energy losses, mechanical energy loss. Professor, I thought you said energy was conserved. It is conserved, but the form that we're taking care of, bookkeeping on, mechanical, can be converted through friction out of the mechanical energy conservation equation, and it just makes things warm. It just heats it up through friction. So that would be an example of a loss. How about a gain? Well, you put a pump in there. So you could have a pump would be a gain. You could have maybe a turbine be a loss. So a device that extracts energy out of the flowing fluid, like a turbine, hydraulic turbine, or a pump. Or you could have just some frictional losses. Frictional, they could be major losses. So how do we modify Bernoulli's equation? Well, we write it. What's your favorite form? Do you have a favorite form already? P, energy per unit volume. Cap H, energy per unit mass. Lowercase h, energy per unit weight. Which form do you like? First, second, or third? All right. We have a split, so we'll just pick third. So we're going to say that we have the inlet pressure divided by rho g plus V1 squared divided by 2g plus Z1, which is the elevation in a gravitational field. You have to get the coordinate system right there. Plus, here we're going to have any head gains that we see. Where would you find a head gain? Pump. Okay. Equal to P2 divided by rho G plus V2 squared divided by 2G plus Z2 plus any head losses. And sometimes you break those into devices that you really wanted, like a turbine, which extracts it, and I'm using some energy somewhere else in the system. And you just have some head loss due to the friction. So this could be on purpose, and this could be just major and minor losses due to friction. F-R-I-C-T. All right. Somebody says, you passed fluid mechanics. I want you to focus on writing an expression for the head loss due to straight run in a long pipe. I got some frictional losses in a straight run of a long pipe. Can you do it? How do I calculate that head loss, HL, for straight run in a long pipe? Professor, this is unfair. First lecture, you're supposed to be kind. Why do you ask hard questions? Hey, it was a long break. I didn't even know where UTSA was. My brain has been flushed. All right. Well, how about a friction factor? Length of the pipe divided by the diameter of the pipe times either the velocity pressure or that velocity head in energy per unit mass, or the velocity head in terms of the elevation head, right? The traditional head. So that would be B squared divided by 2G. And so it depends, we're not changing the diameter. We have one velocity through that long run, okay? How many people? Familiar equation, seen it? Yeah. You can write this equation in terms of a pressure loss as well as a head loss, where this head, cap H, is energy per unit mass. The pressure loss is energy per unit volume. The way I've written it, it's energy per unit weight. So how do I get that friction factor F? Well, it's a function of the Reynolds number and the relative roughness for the pipe. True? Remember that? And that Reynolds number, okay, good question. What is the definition of Reynolds number for flow in a pipe of diameter D? Rho V D over mu. I'm glad to see a lot of people rolling up their sleeves, checking their tattoos to see that equation. Nice. Other one you can put is 4 m dot divided by pi d mu. Either you could put it in terms of the velocity in the pipe or the mass flow rate through the pipe. Either way, both of these equations are exactly consistent. But you should be able to calculate the Reynolds number. Once you have the Reynolds number and they tell you something about the roughness of the pipe, you compare it to the diameter pipe, you have the relative roughness. How do I get the friction factor? Go to the tables or go to the chart. This chart. In the United States, we call it the Moody chart. He published a paper, and we recognize his contribution, but probably in Russia it's a different name. But a similar plot. So we come in here, we have the Reynolds number on the x-axis. We have a different line for different values of the relative roughness. Here's maybe one. And you say, oh, I'm at this Reynolds number, that roughness, read off the friction factor. I'm going to come back to this chart. I encourage you to really study this chart, but I'm going to say that you are able to do that. So now I could calculate that here, this HL. How would we do it? Friction factor, just know how to calculate. Go to the Moody diagram if it's turbulent flow. If it's laminar flow, that's easy, 64 over Reynolds number. That's also, it's on here. There's your laminar flow, and there's your 64 over the Reynolds number. Then you have the length to the diameter, and then that whatever head, that velocity head, so that v squared divided by 2g, and that's how you would calculate it, wouldn't you? Okay. Homework problem 1. First of all, make some notes and changes. Change the word decreases by 400 feet to increases by 400 feet. So the pump is pumping stuff uphill, not downhill. All right? And so it's going uphill, and the inlet to the outlet of the pipe, there's an elevation change of 400 feet going up. Also, they said, check it out for, 10-inch, 12-inch, 16-inch, 14-inch pipe. Add these two, 18-inch and 20-inch. And the initial cost to put that pipe in the ground, $175 a foot for the 18, and 20 inches is $195 per foot. That's the initial cost to put it in the ground. I want you to do it by hand, and I'm going to spend some time remaining in this class talking about it, doing it by hand, as well as by Excel. What do you mean by Excel? You can do it by hand, you can do it in Excel, and then guess what it allows you to do is change the diameter, maybe avoid all the tedious calculations because you built it into let the computer do the tediousness. Okay? Turn in the Excel by emailing it to utsathermal@gmail.com, and in the subject line put your ABC123. I think you know to substitute yours instead of the generic there. Tell me what class. We already know it's ME43, so that's the same for everybody, as well as that it's homework number 1. So that's attachment. Now, the hand calculations, you either bring the paper copy in and you put it in a stack. That's fine. Or you can scan it and keep your paper, but you have to have the ability to scan it somehow and send that as the attachment to the same email. What's the advantage? Why is this recommended? I have no idea, with this many students in this class, how I'm ever going to get graded homework back to you promptly. Oh, it'll come back, but it'll be kind of like the average UTSA professor. All right? What does that mean? You'll get it back, but it'll be, it's working on it. I promise to work really hard to get graded exams promptly back, but I just know right up front homework's going to be. So, attach it, keep your original homework. How's that? Not bad? All right. What time does this class end again? We got about 15 minutes? Yes, we do. We have about 15 minutes. So let me do this. What is this problem? Chapter 1 that you're supposed to work on, and how do you solve it? So they have this pipeline, and they want to carry 4 times 10 to the 6, 4 million gallons, G-A-L, gallons of water, so it's H2O, per day through this pipeline. So right there, 4 times 10 to the 6 gallons per day. Okay? What did they just give us? Did they give us mass flow rate, weight flow rate, volumetric flow rate? Volumetric flow rate, didn't they? Okay. So this would be AV. They said it's water. I know that water has a density of 1,000 kilograms per meter cube, but we're going to work in gallons and feet and BTUs if we need to and all that, right? Pound force and pound mass. What's the density of water? That is great. If you knew that, I should go around and give you a little star like in kindergarten. Great job, you know that. 62.4 pounds per cubic foot. Now, rho, that's mass density. Is that LBM or LBF? LBF. What is gamma, the weight density of water? G times rho. Professor, if I could answer, that's the same question I asked about 5 slides ago, okay? So think about that. Think about it. If I take 1 cubic foot, everybody could take their hand, there's a foot, cubic foot. It weighs about, the mass is 62.4 pounds of water in that cubic foot. Can you imagine going and getting maybe that much weight somewhere and lifting it? What would it feel like? Can I lift it with my pinky? You know, is it that most people in this class or nobody in this class could lift 62.4 pounds? but most of us would feel it. It would be a lot to lift, true? Okay, so we know how much mass is in there, 62.4 pounds mass. How much is the weight? Am I looking at trying to lift, you just take 62.4 and either you're going to multiply by 32 or divide by 32 or just leave it alone at 62.4. So there's your three options. Maybe I should ask that question seriously. So I can do the 32 times 62 and 1,984 pounds. Or is the answer 62.4, 32.2 divided? Is it 1.94 pounds or is it 62.4 pounds? What is the weight? 1 cubic foot of water. I fill it up. I said, hey, the mass in there is 62.4 pound mass. Can you lift it? Well, who thinks they can lift 1,984 pounds? That's a ton. My pickup truck only carries a half a ton. You got to buy the super duper model to get the 1 ton capacity. True? Nobody's lifting that. All right, 1.94 pounds. Can you lift a little bottle of soda there? Ooh, he did. You know what? I think there's going to be no problem. All right, 62.4 pounds. Which is the right answer? 62.4. Please, please, please. That's a good thing to get down in your mind and psyche and everything else, and it answers the other questions I asked earlier. All right, now I need to get back to this problem and not get diverted. They tell you the temperature, you can get the viscosity. There's a table in the back of the book for the viscosity. You can get the temperature of water at that 55 degrees F. You can work with the units. They tell you that the length of the pipeline is 3 miles. How many people know how many feet are in a mile? Very good. 5280. Excellent. 5280 feet in a mile. See, we're conversant. Sorry if you're from Mexico. You're probably being tortured right now. It's like, I'm going back to Mexico. I'm leaving this alone. Is anything in miles in Mexico? You know, there's one interstate highway in the United States that's metric. And it comes from Mexico directly into the United States, somewhere in Arizona. But it's all metric. The speedometer is all metric. Anyway, it's a little known fact. One highway in the United States is truly metric. Okay, I need to keep going. And the change in elevation. So the final elevation minus the initial elevation is an increase of 400, not a decrease, increase of 400 feet. The cost to install the pipe, so if you put in a 12-inch pipe, the diameter of the pipe is 12 inches, then it costs per foot is $115 per foot. So that's fine. Power cost, so the cost for the power is $0.075, so 7.5 cents per kilowatt hour. How do we write that? Well, cost per the energy, maybe something like that. And you want this to go a lifetime of 15 years. You only bury the pipe once, buy it and install it once, and that's the cost to put it in the ground once. But then every year, you're going to have to provide electricity to run the pump, to push the water, overcome the friction and bring it up the elevation, true? To overcome both the friction and the elevation. So the pump efficiency of the pump is 56%. What is the most economical pipe diameter? So not the 12, not the 14, not the 16, maybe the 18, maybe the 20, the two numbers I gave you, but there's 5. You got to repeat the calculation 5 times. Excel, please. Do it once by hand and then put it into Excel and repeat it by changing the diameter. Got it? All right. So how do we do this? We say we're going to do a modified Bernoulli to account for the power the pump puts in. What form do you want to work in? Head, energy per unit mass, or pressure? Your choice. You can pick one. Okay? Stay with head, elevation like head. Okay, so we're going to have the pressure at 1 divided by rho g plus 1/2 V1 squared, plus V1 squared divided by 2G plus Z1 is plus any head gains due to pumps. That's what I like to do is, I know I like to write long subscripts, then I shorten it a little bit. This is the head that's getting into the fluid. That's the head gain by the fluid going through the pump. It's not the same as how much energy the electricity supplies or the motor supplies to the pump, because there's the efficiency of the pump of 56%. All right, and then we're going to have the pressure at the exit, and then we have rho g, then we have the speed at the exit, 2g, plus the elevation at the exit. Okay, and then we're going to have some head loss due to the major loss of friction. How's P1 and P2 compare? No information about the difference pressure. It's the same pressure. How about the speed? Are we the same speed inlet, same speed outlet? So what we have is we have that the head gain that the pump has to supply to the fluid is equal to the change in elevation, it had to lift it, plus the head loss. True? So you go and you do the work to say, how does the equation for this head loss? That's F L over D times 1/2 V squared, the V squared over 2G, right? So you do need to know the speed in the pipe, and so if I change pipe from 12 to 14 to 16-inch diameter, it changes the speed. Great for Excel to update. This friction factor, you're going to have to go, you want to go by hand to the Moody chart. But I'm telling you, you don't want to do that too often. Somebody must have coded up the Moody chart. It's in chapter 1. Go to this website, type in the search engine Excel and ME, you'll go to the University of Alabama website. The person over there teaches a course in energy systems design. You could have called it thermal systems design, energy systems design. You could see that he's interested in pipes and piping systems, pumps, pumping systems, heat exchanger design. So there's a few things that are free. Download the thing over here. And the Churchill friction factor equation is what you want to use. Somebody says, I don't know how to download this and add it in. Go to this, type my name in, look for this Excel tutorial. And it basically how to find, download, set up, and use thermodynamic properties to evaluate steam. It's a cell add-in, and it's going to be the same thing for this other add-in. So get it built in. Professor, I don't have a computer. It's 2016. I don't know what to say. Can you get one? Otherwise, it's going to be a really painful semester. You've got to be able to put in add-ins, and there's really no UTSA resource because you add it in, then tomorrow you come back to the same computer. Sorry, been wiped. True? All right. So you'll be able to get this as one call. Let me show it to you. So I'm just going to quickly bring it up here. You'll want to have equal to FRIC, you can see it right there, Churchill. So hit tab there. And then if you want more information, hit this little function right there. It gives you the argument. So give me the first parameter, which is the ratio of the roughness of the wall divided by the diameter, epsilon over diameter. The second parameter is the Reynolds number, and it gives you back that friction factor. Otherwise, you got to look it up all the time by hand. That's tedious, true? Check it by hand with the chart. You'll see it's pretty good if you implemented it correctly. Let's go back to here. This part's easy. So once I have the head that the fluid has to get added to it by the pump, true, what you can do is you can calculate the power. The power W dot fluid is this H fluid times some gravimetric flow rate. Okay, the gravimetric flow rate. Well, if I took the rho g times AV, does that give me the gravimetric flow rate, the volumetric flow rate times the weight density? It really this type of problem is great. Forces you to challenge you, like, what are these terms? Professor, I love plug and chug. Ain't the class for you. Find another class, right? But that's the way it is in engineering. You got to own what you're calculating and not mess up. True? All right. All right, so that gives you, that's how much power needs to get into the fluid, but how much do you have to supply to the shaft to get it into the fluid? You have to supply more to the motor has to supply more. So the W dot electric is 1 over the efficiency. Where is that efficiency? Right here. Of that pump times W dot fluid. It's a good review of some fluid calcs that you did, hopefully. Once I have that electric power, monthly I pay the utility bill. Let's say I pay it continuously for the next 15 years. So basically I say 15 years of time, multiply W dot times the time of 15 years, and that's how much energy that I have to purchase for the electricity. Isn't it true? And if I multiply by the cost per unit energy times that energy I just calculated, how many kilowatt hours? Yes, you're going to have to struggle with units. You're going to get it into kilowatt hours. Okay? The book has a lot of them. One of the things I did, remember that Thermo 1 equation sheet that you had? I even taped it, the front page of my textbook, so I could quickly go back and forth. Okay? This is years ago. I did this probably, many years ago. So you need to be able to convert units. But that'll give you how much is the cost of the electricity. You add that to the cost of burying the pipe, and you see over a 15-year period which one's best. Let me give you one benchmark for comparison. Last minute, you've been very patient. This is the run. If you want to write these numbers down, you can do that. Or you can, I'll post this up there. But the bottom line is, that's the 20-inch pipe. I did it for the 20 right there. So I had to change the diameter of the pipe in inches. I have it set. That's the beauty of Excel. Put in the units that you like and the things that you like and let it do the conversion to feet and everything else. This was the input of the flow rate. This is how much electricity cost is going to be for the next 15 years. What is that number? $3,887,000. That's just the calculation. $3 million for the next 18 years. And if it costs $195 per foot to put it in the ground, then the installation cost is $3 million. And the total cost over the 15-year life is that much. And I even broke it down so that the fraction of the total cost of the electricity is 56% and installation cost 44%. There's a lot of little tidbits you can get. But I give that to you as a helpful thing, okay? Here is the calculation of the friction using that friction Churchill. Right? Is it too much to ask? Can you get it done by Thursday? Very good. Thank you very much. We'll see you later.